So whether we have a normal residual or not, we can use a normal probability plot, PP curve. So this in this particular case, if the residuals are along this straight line, that is an indication that the residuals are following a normal distribution. On the other hand, if it is like this, then it means that we have the residuals as positively skewed. Similarly, if the pattern is like this, then it means that the distribution is heavy tailed distribution. Remember, note that normal distribution does not have heavy tail, but other distributions, including T distribution, Gompertz distribution, all these are heavy tailed ones. So if our residual distribution is heavy tailed like this, then it means that we do not have normality pattern. Now these residual plots are not enough in themselves. We need statistical tests. We have a statistical test. We have a large number of statistical tests for non-normality, but the most popular one is the Raki-Bera test. Carlo Raki and Anil Bera. So in this test, both the skewness and kurtosis of a distribution are used together. So the formula is given here. S is the skewness and K is the kurtosis. If skewness is 0 and K equals 3 for a normal distribution, then the JV statistic is 0. That means we have a normal distribution. If S equals 0 and K equals 3. Otherwise, if the p-value for this statistical test is greater than 5%, then we cannot reject the null hypothesis of non-normality. Okay, the hypothesis of non-normality. Sorry, if the p-value is greater than 5%, then the null hypothesis. See, the null hypothesis here is not non-normality but normality. That is, the residuals are normally distributed. That we cannot reject. So once more I shall tell, if the p-value is greater than 5%, then the residuals are normally distributed. There is no problem of non-normality. And for that matter, in advance, I shall give you one information for all the model adequacy tests, our p-value must be greater than 5%. If our p-value is greater than 5% for all the model adequacy tests, then it means our model is adequate. There is no problem at all. That model we can use for our hypothesis testing, and the further we can go for forecasting. So the p-value must be greater than 5%. So here also it is like that. Now, what are the remedies if we have non-normally distributed arrays? So one thing, we have to modify our theory and try that. Then see whether there are any omitted variable and whether there is any outlier. Also, we can modify our functional form by taking some variance transform steps, such as getting square root, exponentiation, logs, etc. So we can try for taking logarithmic transformation or taking the square root of the data or getting a power of that particular data and so on, and try to go. So that way we can modify our data set. Now the next one is multicollinearity. As I have already told you, multicollinearity refers to the relationship among the independent variables. The most problematic multicollinearity is when the variables are perfectly correlated. In that particular case, the estimation will stop, cease, and the computer will tell that it cannot proceed further. And we have the condition where the estimation approaches singularity. Approaches singularity, or this singularity means that we cannot estimate the particular model. So if we have perfect multicollinearity among the independent variables, then it is not possible to estimate the model. So remember, this is a sample problem, and therefore we have to do something with the sample to avoid this particular problem. We will come to the remedies later. Now, multicollinearity is always there among all the data sets, and it is a problem of degree, not just the presence. So that means multicollinearity can appear in different degrees. We have the two extremes. At one extreme, we have perfect multicollinearity, and the other extreme, we have no multicollinearity at all. Between these two limits, we have different degrees of multicollinearity. So I shall tell you about these three cases now. So let us now consider the case of no multicollinearity at all. That is, all the data sets are independent of each other. No correlation at all among the X variables. That means the X variables are orthogonal to each other. So in this case, even if we suppose we have two independent variables x1 and x2, if we go for a multiple regression, then the regression coefficients will be equivalent to a simple regression coefficients. That means if the explanatory variables are not multicollinear, then we can go for bivariate simple regression. Now remember, this is the only case we can go for bivariate simple regression. In all other cases where there is some multicollinearity among the independent variables, we must go for multiple regression. So if there is no multicollinearity, then only we can go for simple regression of bivariate one. I have seen many researchers considering several variables, but taking two variables at a time and giving a large number of bivariate regressions. This practice is wrong. We have to go for multiple regression, not the bivariate one. Bivariate regression is possible only if we have no multicollinearity among the independent variables. In that particular case, remember, if we go for a multiple regression, the multiple regression coefficients will be the same as the coefficients from a bivariate regression. That is the case. So the next case is the other extreme, that is the perfect multicollinearity case. So this is the singularity problem. In this case, take any two variables x1 and x2, and perfect multicollinearity appears if x1 is equal to kx2, where k is not equal to 0. That is, k can be any number, positive or negative. Maybe x1, if k is equal to 1, then x1 is x2. If k equals 2, then x1 is twice x2, and so on. In that case, we have perfect multicollinearity and we have the singularity problem. We are not able to estimate the parameters. The computer will crash. Between these two cases, we have imperfect multicollinearity. This is the more common problem among most of the independent variables. This is there, the imperfect multicollinearity is there, and that is why we have to go for the multiple regression. Here, we are able to estimate the parameters and they are unbiased. But the problem is with their standard errors, that is their variance. The variance is not the minimum. The variance is not the minimum. Now, if the variance is not the minimum, then what are the implications? That is, if there is high correlation among the independent variables, we will have an inflated variance of the estimated, the parameter estimate, beta k hat. In this case, the t ratios will be lower because we have a higher variance or higher standard error. Therefore, the t ratio will be lower. And that means the beta k hat will become insignificant. At the same time, we find R squared tending to be very high. And we will have a significant F statistic also. So multicollinearity is there when we have significant, that is very high F value, very high R squared, but very low T values. Remember, if we have very high R squared, if we have very high R squared, then the F value will be very high. But at the same time, if we have very low T ratio, then that is an indication of multicollinearity. Along with that, sometimes there may be a change of the sign for some variables. Some variables will change sign. We may be expecting positive sign, but we find negative sign for that. On the whole, the estimates will be unbiased, but we will have these particular problems. Now, for the tests, for the indicators for multicollinearity, I am reporting two indicators. One said to be the most useful single diagnostic guide by J. Johnston in his textbook on econometrics is the variance inflation factor. I'm not going into the details of this because we don't have time. But in most of the packages, we get the variance inflation factor. How do we interpret that variance inflation factor? If variance inflation factor is close to 1, that means there is no multicollinearity. But if it is greater than 10, then it is problematic. And usually we take this 10 as a yardstick. Any VIF greater than 10 is said to be indicating a problematic multicollinearity. Otherwise, the multicollinearity is not a problem. This VIF of 10 indicates that the probability is severe. That is 90% of the variance of xj, one variable is explained by other variables, other independent variables. Even though the usual criterion is a VIF greater than 10, in small samples, we have to consider a VIF of about 5. So these are the two values that we have to keep in mind. Then corresponding to the variance inflation factor, we have another measure called tolerance, which is the reciprocal of the variance inflation factor. If the tolerance equals 1, that means the variables are unrelated. If it is equal to 0, then that means the variables are independent variables are perfectly correlated, because the variance inflation factor will be an infinite one. Now the second indicator is given by Wellesley in 1991 in terms of what is called a condition index or condition number. Some of the textbooks refer to these Wellesley's indicators also. And this, both the index and the number, condition index and the condition number, are taken from the eigenvalues of the matrix of x prime x, where x is the data matrix. Now, from the data matrix, from that x prime x, we will have a number of eigenvalues, lambda 1, which is greater than lambda 2, and so on. That is the eigenvalues given in ascending, in descending order, so that lambda 1 is the highest eigenvalue. Then the condition index is defined as this lambda 1 divided by a particular lambda j. J can be 1, 2, 3, and so on. Now in Stata and SPSS, the condition index is given in terms of the square root. Now we have another measure called the condition number. This is the square root of the maximum eigenvalue, that is lambda 1, and the minimum eigenvalue, that is the last lambda 1. That is, it is the square root of maximum Cij. So these two indicators are used for multicollinearity measure. And they have given this criteria for multicollinearity test. That is, if the largest condition index is 5 to 10, that means there is no problem. If it is between 30 to 100, then there is some problem of multicollinearity. If we have the largest condition index in terms of more than 1000, then the multicollinearity is a severe problem. Now, what are the causes of multicollinearity? The usual sampling mechanism can generate multicollinearity. That is purely constructed design and measurement scheme for the limited range of the sampling mechanism. Then statistical model specification also can generate multicollinearity. That is adding polynomial terms of the trend indicators. If we take, say, suppose we have one independent variable x1. If we take the square of that, x1 squared, or cube of that, then there will be multicollinearity. Then if there are too many variables in the model, that is, if the model is overdetermined, then that also can cause multicollinearity. Then finally our theoretical specification can go wrong and cause multicollinearity. Now, what are the remedies for this? One remedy is to increase sample size, and it can work sometimes, not always. Sorry. Then the other case is to omit the collinear variables. Now, suppose we have three variables x1, x2, x3 as collinear, multicollinear. If they are highly collinear, then we can omit two variables and go with the regression of having one variable only. But there is a problem with this. If we omit the variables, then there will be omitted variable bias, and that will lead to specification bias, specification problem. And moreover, if we want to have differential impact size of different variables, then we cannot omit variables. Suppose we have the variables income and, say, wealth in a consumption function. Consumption as a function of income and wealth. Of course, there is multicollinearity between the two independent variables, income and wealth. But if we want to find the marginal effect of income and wealth separately, then we should have both the variables in the regression. That is the case. So we cannot go for omitting the variables. Then the another alternative is to go for constructing some scale. That is, we can find an average of the three variables x1, x2, x3, and get a representation of all the three variables. But the problem of differential marginal effect size remains there. So it is not advisable to go for a scaling technique also. Similarly, we can go for a scale in terms of factor analysis. If we have a large number of variables, large number of independent variables, multicollinear, then we can go for a factor analysis. That is, we can go for what is called a data reduction. That is variable number of variable reduction. We can go for a factor analysis in specifying a few factors to represent all other variables, all the variables. But here also we have the problem of getting the differential marginal effect size of each variable. So that also is not advisable. Then what we can do is to constrain the estimation, but that is setting the value of one coefficient relative to another. That is, get some relative measure. If we have two variables x1 and x2, which are collinear, then we can take a ratio of these two. But there also we have the problem of not getting the differential impact. So most of these remedies are not advisable. So we go for the last one, that is just cross our eye towards multicollinearity problem. That is just ignore it and report the adjusted R squared and say that we have to retain these variables in the model. Otherwise, there will be omitted variable bias, and we will not be able to get the differential impacts. So, in general, the advice is to ignore multicollinearity. Now we come to the model specification problem, that is the specification error. So the specification error, we have four types. This I have already told you earlier. That is, we may exclude a relevant variable, or we may include an irrelevant variable, or there may be functional form misspecification, or there may be measurement error or misspecified error tail. That is, we may have too many or too few variables. Now, what are the implications of that? What is the implication that if we include a variable in our specification that do not belong to that is including a variable that is irrelevant to our model. The implication is that there is no effect on our parameter estimate. The OLS estimates remain unbiased. There is no problem at all. On the other hand, if we exclude a relevant variable from our model, then the OLS estimates will be usually biased. So these are the two implications of the first two problems. So the first one is excluding a relevant variable, that is underfitting bias. Suppose the true model is with the two variables x1 and x2, but we estimate the model only with one variable. So the misspecified model will be a biased one. In the second case, our true model is having only one variable, but we estimate including an irrelevant variable. In this case, actually, there is no problem at all. Both beta 1 and beta 2 will be estimated unbiasedly. But there is a problem for the variances of beta 1 and beta 2. If x1 and x2 are correlated, if there is multicollinearity between x1 and x2, then the variances of beta 1 hat and beta 2 hat will not be minimum. We know it is an inflated one. The variances are inflated one. So the estimates are not efficient. They are unbiased, but they are not efficient. The third type of the function, the misspecification occurs when we go for some functional form misspecification, incorrect functional form. For example, if the true regression model is log linear and we go for a linear regression, then we are having this problem. And actually, if we are committing an incorrect functional form specification, then it can lead to autocorrelation or heteroscedasticity or both. Now, what about the testing for the specification error? We have a research. Research is given by Ramsey, and this is said to be Ramsey's regression specification error test. RE, regression specification error test. So the null hypothesis is no specification error. And if the p-value is greater than 5%, that means our model does not have any specification problem. Remember, I told you earlier, all the model adequacy tests should have a 5%, should have a greater than 5% p-value. In that case, our model will be adequate. Now, we have two more assumptions, and these two assumptions are related to our spherical error assumptions. One is about the no heteroscedasticity assumption of the error type. That is, we have an assumption of homoscedasticity. Variance of ui is a constant sigma nu squared. And the second one is that there is no serial autocorrelation. So we may have serial or autocorrelation problem if the covariance among the residuals or the error tail is not zero. Now that we are taking the first case, that is the heteroscedasticity assumption. Now see, here I have given three distributions. And here we have the mean. In all the distributions, the mean is given here. So what are the implications of these distributions for the variance of that particular random variable that we consider? Anybody can tell me? Don't take much time. Anybody? Can you tell me the implication for variance of the random variable here or in this case? Anybody?
It
Sir,
is mean
in the
reverting, sir.
What is
sir, in
it?
the first case, the variance
Ah,
is less, whereas
ah,
in the last case, the variance is more.
very high. And this is an intermediate one, right? So
Yes.
here the variance pressure is very small. That is, all the values are very close to mu. That is why we have a small variance. Here that is not the case. the values are distributed away from mu considerably, substantially. So the variance will be very high. Now, if we have the explanatory variables like these, x1, x2, and so on, and the error variance is given like this, then this is a homoscedasticity case. That is, the error variance is the same with respect to both the independent variables. So we have the case of homoscedasticity. On the other hand, if we have a case like this for the three independent variables, x1, x2, x3, the variances are different. The error variances are different. So we have the problem of heteroscedasticity. Now, if we have the problem of heteroscedasticity, then the residuals will have a fan or a funnel shape like this. This is a fan or funnel shape, or more clearly like this. So here we have a funnel shape or a fan shape. Here also we have a funnel or fan shape. That is not the case here. Here the variance is constant. So we can have a diagrammatic representation of heteroscedasticity if we plot residuals against the independent variable, and the residuals are like this, like a fan or funnel. Now the implications of heteroscedasticity are this. Now here also, just like our multicollinearity problem, the parameter estimates are unbiased and they are consistent also. That is, the asymptotic property also is available. But the problem is they are no longer the best estimator. Their variances will be very high. That is the problem. So in general, they are not blue. That is, they are not, we do not have the minimum variance property. They are not efficient estimators. So if they do not have minimum variance, then we will not have minimum standard error, then that will lead us to wrong inference. And we will have invalid confidence intervals also. Then there are different types of heteroscedasticity. We may have additive heteroscedasticity or multiplicative one, or an arched one, which is a time series problem. That is autoregressive conditional heteroscedasticity. That is the arch problem. So such a type of heteroscedasticity also we have to see as a for the model adequacy among the model adequacy tests. So we will come to this later. So when we take up the time series analysis, we will be seeing this arch case. Now, what are the causes for heteroscedasticity? Earlier, we have already told if there is any omitted variable case or improper functional form that can lead to heteroscedasticity or autocorrelation. Then there may be some learning behaviors across time among the economic agents that can also lead to heteroscedasticity. Then changes in data collection or definitions. Then outliers or some breakdown in the model. So these are the causes of heteroscedasticity. Then for testing, we have a large number of tests for heteroscedasticity. We can use the Ramsey reset test itself, or we can go for some other tests. Among all these, most popular are the Bruce-Pagan test and the White test. Now, I shall give a comparison between the Bruce-Pagan and the White test. The Bruce-Pagan test will detect the linear forms of heteroscedasticity, whereas the white test allows for non-linearities also. So it is better that we go for the white test. Now, what are the remedies for heteroscedasticity? We have two remedies. They are the indirect and direct remedies. The indirect remedies come in two forms. That is, either we can re-specify the model and then re-estimate it, or within the same model, we can use what is called White's robust standard error, which is a heteroscedastic consistent standard error, a standard error that is consistent with heteroscedasticity. So the first such standard error was given by White in 1980. And that is why it is called White's robust standard error. So we can use the robust standard error if there is any heteroscedasticity problem. The second remedy is a direct one, that is, we go for another least squares method, which is called generalized least squares method or weighted least squares method. In this particular case, what we do is we adjust the data set completely so that we will get a homoscedastic error tail for the given data set. With that homoscedastic data set, we go for our estimation as usual in the OLS. So that is the generalized least squares or GLS method. Now about the robust standard arrays, remember the robust standard arrays have only asymptotic distribution. So they have only asymptotic justification. So if we have a small sum, then it is better that we do not go for the robust standard error. The inference will not be correct. Then coming to the GLS, generalized least squares method, as I have already told you, what we do here is we go to transform the model into another one with a homoscedastic error tail. So that is we give some weight to the data sets. That is why it is called weighted least squares, and transform the entire data set so that the error tail will become homoscedastic. I'm not going into the details of this one because it will take a lot of time. So just remember, we have the direct measure, we have the direct estimation method in terms of GLS or weighted least squares method. Now coming to the autocorrelation problem, we know this shows that the arrays are not correlated over time. That is our assumption shows that the correlation, there is no autocorrelation among the error types. Now if we go for a residual plot, a diagrammatic representation of our residuals plotted against time, then if we find a cyclical pattern, then that is an indication of positive autocorrelation. Positive autocorrelation. Now we have different types of autocorrelation. One is the usual autoregression, or we say autoregressive process, AR, and then we have another one, moving average process. I shall give a small introduction to these cases because again remember in the time series analysis we will be discussing these autoregressive and moving average processes. Combining this, we will get what is called the ARMA, autoregressive moving average process. So an autoregressive process says that error term or the residuals are related to their previous values. Here ut, the error term at time t is related to its own previous value. That is why it is called an auto regression. This is a regression of ut on its own past value. So hence auto regression. So this is said to be a first order autocorrelation or auto regression because we are using only one lab, t minus 1. We are using only one lab. We can have higher levels of auto regression. For example, if we use 2 labs, then we have an A of 2. And in general, if we use P labs, then we have an AR P. In all these cases, remember the current error term is regressed on its own past values, all the past values. And that is why it is called auto regression. Now, the moving average is different from the auto regression in that the current error term is regressed on the current error term. This epsilon t is a disturbance, okay, and some other random error term and its past one, that is epsilon t minus 1. So our residual we are regressing on and an error, a random error term and its past values. Here we are using one lab, therefore we have an MA1 process. We can have an MAQ with the Q lab, and that is we are using the error term epsilon t minus 1 and so up to epsilon t minus 2. So our this disturbance term is a function of some random error and its own past values. Now we can compare AR and MA process like this. So we get what is called an ARMA PQ model. That is the error term is regressed on its own past values. That is the auto regression, and then some other random error term and its past values. So this is autocorrelation.
Sir, can you explain the previous slides one more time?
This one.
From ARMA itself.
ARMA itself.
From ARMA onwards, sir.
ARMA onwards. That is this one. Or AR.
Okay, sir.
You mean AR?
AR.
See, AR means. See, AR means we have our error term, which is regressed on its own past one, ut minus 1. Okay, that is an auto regression or auto correlation. ut, the correlation between ut and ut minus 1. So we can have higher ODs, AR2 or ARP in general. Everywhere we have ut regressed on its own past values. And remember, we will have an error term for that also. That is given by this epsilon t. Now, the moving average process is given by specifying this ut in terms of this t and its past value. That is epsilon t and its past value. That is the MA1 process. If we have more log for epsilon values, epsilon variables, then we have MAQ model. Now we can combine this ARP and MAQ as an ARMA PQ model. That is, we have ut in terms of its own past values and the random error term and its own past values. So this is the ARMA PQ model. We will learn this when we come to the time series class. So we have already this autocorrelation, AR or MA. Now the implications are just like our heteroskedasticity. If there is autocorrelation, then the estimates are still unbiased, but they are not blue. That is they are not efficient ones. The variance of the estimate is not minimum. Now the causes, this also we have already seen in the case of the heteroskedasticity. So if there is an omitted variable, wrong functional form, or lag defects, or if we are doing some data transformation, that also can cause autocorrelation. For example, differencing. If we do the differencing, then that can cause autocorrelation. For testing, we have a simple measure called Durbin-Watson statistic or D statistic. And this D statistic lies between 0 and 4. If D is around 2, then that means there is no first order autocorrelation. See, the Durbin-Watson statistic will test only the first order autocorrelation. Higher order autocorrelations cannot be tested by the DW statistic or simply D statistic. And if this D statistic is around 2, that means there is no first order autocorrelation. If D is less than 2 or close to 0, then that means there is positive autocorrelation. And if D is greater than 2 or close to 4, that means there is negative autocorrelation. This I am giving. In this case, we have 0, DL, DU, then this, oh, okay, I shall give the next one. Here we are including all the entire limit that is between 0 and 4 for the D statistic. And we know that this estimated D statistic we have to compare with the table value for the D statistic. In the table value, there is a lower limit and an upper limit where the test is inconclusive. So we cannot get to a conclusive result if our estimated D statistic lies here. Similarly, there is an inconclusive range between 4 minus du and 4 minus dn. Otherwise, if our D statistic is around 2, then there is no autocorrelation. So what is our null hypothesis? Null hypothesis is there is no autocorrelation. No autocorrelation. So if it is close to 0, then that means there is positive autocorrelation. And if it is close to 4, then that means there is negative autocorrelation. So these are the cases. Here we have all the 4 cases. In general, remember, if the D statistic is around 2, that means there is no first order autocorrelation. Now, this is only for the first order autocorrelation. For the higher order autocorrelations, we have some other testing procedures. And mainly we have one testing procedure in terms of what is called Bruce-Pagan autocorrelation test. So those autocorrelation tests we have to do. We can do in Gretel and similar statistical software. So we will do that in our afternoon session. Now here, this doesn't matter. Okay. Now suppose in this particular case, the D statistic is estimated as 1, and 1 is much less than 2. And therefore, we can conclude that there is positive autocorrelation. Now, I told you one problem of the Durbin-Watson statistic that it is dealing with only with the first order autocorrelation. Now, the Durbin-Watson statistic is inapplicable or it fails in interpretation of autocorrelation if there is a lagged endogenous variable in our model. So, DW statistic in that particular case, the DW statistic will approach a value of 2 showing that there is no autocorrelation even if there is autocorrelation in the results. So that is the problem with the Durbin-Watson D statistic. That is, if we have a lagged dependent variable in our model, we cannot use DW statistic. In such case, for testing the first order autocorrelation, we have another test given by Durbin in terms of Durbin's H. Durbin's H has a standard normal distribution. Therefore, we can compare the Durbin's H with our usual 1.96 value. At 5% significance level, we know 1.96 is the critical value. If the Durbin's H is greater than 1.96, then we will reject the null hypothesis of no autocorrelation. Otherwise, if Durbin's H is less than 1.96, that means there is no autocorrelation. That is, we are not rejecting the null hypothesis. Now, the remedy, as I told you, as in the case of the heteroskedasticity, we have the same generalized viscous method, but in a different format. The GLS we apply here in terms of either a first difference method, that is, we take the first difference of our x variables and the dependent variable, and then regress delta y, the first difference of y on the first difference of our independent variables. And here we are assuming that the autocorrelation coefficient is equal to 1. There is another method which is called a generalized difference. In this particular case, we should know the value of the autocorrelation measure, that is rho. This is the Cochrane-Orcutt method. I am not going into the details of this. What we have to do is, first we estimate our variance and get the residuals. Then using that particular residual, we regress the current value of the residual on 1. Okay, we are regressing on one previous value of the residual. And regressing like this, we will get an estimate of the autocorrelation coefficient. That is the rho hat. Then we use this rho hat in a generalized difference formula like this. We multiply by t minus 1 with this rho hat. Also multiply x t minus 1 with this rho hat, and then take the generalized difference like this by t minus rho hat by t minus 1, and then regress this on a new constant and a new independent variable obtained by this difference. And then what we have to do is substitute the values of B1 and B2 into the original regression. That is this one here. And then we get a new measure of rho hat. And then again do this particular generalized difference regression. And go on like this until the rho hat no longer changes. Then we in that particular we have arrived at what is called the convergence in the result. So that particular result we can obtain. So I'm stopping here.